So, good evening. Today I am going to discuss fitting of Poisson distribution. I have already discussed fitting of binomial distribution in my previous class. So, today I am fitting of Poisson distribution. If x follows Poisson with parameter lambda, then we know the PMF of PMF means probability mass function of x is fx, which is equal to e to the power minus lambda to the power x by x factorial, where x is equal to 0, 1 to up to infinity, and 0 otherwise. Now, as before, fx by fx minus 1 is equal to the power minus lambda to the power x by x factorial, to the power minus lambda to the power x minus 1 by x minus 1 factorial. So, this is equal to lambda by x for x greater than 0. So, this implies fx equal to lambda by x fx minus 1 for x is equal to 1 to infinity. Okay. Why x is equal to 1 to infinity? Because x is equal to, if you take x is equal to 0, then this relation doesn't hold, because if not, if my if x is 0, if x less than, when x less than 0. Okay. So, start with the value of f0, which is equal to the power minus lambda. If you look at the PMF function, then you will easily get this thing. If f0 equal to the power minus lambda, we can successively find f1, f2, f3, etc. from this relation. This relation is known as recursion relationship. Recursion relation for probabilities of the Poisson distribution. Okay. So now, to set a Poisson distribution, to set to, uh, to see if a Poisson distribution, if a Poisson distribution fits an observed distribution, we are to calculate the expected frequencies corresponding to different observed frequencies and compare the two series of frequencies. If there is close argument, if there is close agreement, we shall conclude that the fit is good. Here the expected frequency of the value x of the variable is equal to n into fx, which is equal to n into e to the power minus lambda, lambda to the power x by factorial, where x is equal to 0, 1, 2, up to infinity, where n equal to total observed frequency. The computation of the probabilities becomes easy if we use the recursion relation. If we use the recursion relation. For probabilities. When the value of lambda is unspecified, we estimate it by the method of movements. That is, lambda hat, which is the estimated value of lambda, is equal to x bar, that is sample. And proceed as before. Okay. So now I consider an example for illustrate this. Suppose x takes value 0, 1, 2, 3, 4, 5, 6 and more. Frequency is a observed frequency which is equal to 140, 75, 25, 6, 3, 1, 0. So if you look at this data set, then you see that as x increases, frequency also, but frequencies decreases. As x increases, frequencies decreases. So it is a appropriate example of Poisson distributions, because uh, Poisson distributions means as uh, n is infinity, number of trial is infinity, then probability of success is very small, that is close to 0, but np, which is finite, then we can approximate binomial distribution to Poisson distribution. So here we observe that uh, this is a Bernoulli random variables, and the frequency as the value of x increases, the frequency decreases. Okay, so this is the situation. This is the appropriate situation when Poisson distribution gives better results. Okay, so here we see that. So we call the PMF of probability mass function of Poisson distribution. So if we which I already defined here, that is fx is equal to e to the power minus lambda by lambda to the power x by x factorial, where x is equal to 0, 1 to infinity. But here we see that lambda is unknown. Therefore, we need to estimate lambda, and we denote the estimated value of lambda by lambda hat, which is equal to x bar. This x bar is nothing but a sample mean, that is x into a by summation f. F is the total frequency. Here, summation f is 250. If you compute this thing, you get this thing. Summation f, I denote this observed frequency denoted by small f. So summation f is nothing but a 140 plus 75 plus 25 plus 6 plus 3 plus 1 plus 0. So this gives 250, and summation f xf, that is 0 into 140 plus 1 into 75, 2 into 25, 3 into 6, 4 into 3, 5 into 1, and because this is 0, so you need no need to calculate this part. So this means summation x f is nothing but a 0 into 140, 1 into 75, 2 into 25, 3 into 6, 4 into 3, 5 into 1. This gives 160 in total. So this is equal to 0.64. So now if x is equal to, so this is the fitted distributions. The fitted distribution is e to the power minus 0.64 into 0.64 whole to the power x by x factorial, and x is equal to 0, 1 to up to infinity. So now we recall the recursion relation for probabilities, that is fx. This is the recursion relation for probabilities. Fx is equal to, since lambda is unknown and we estimate this lambda by lambda hat. So we replace lambda by lambda hat here. So this is lambda hat by x into x minus 1. And x is equal to 1 to infinity. Here f naught is equal to exp minus lambda hat. So this is equal to exp minus 0.64. This is approximately 0.522729. Please check these values. Okay. So please check this value. Okay, Swarnavo, good evening. Pritam, good evening. Suman Bari, good evening. Sarsato, good evening. So please check this calculation. Tell me whether these are correct or not. And F1, that is 0.64 by 1 into F naught. So this is equal to 0.33746. Similarly, F2, which is equal to 0.64 by 2, 0.64 by 2 into F1, this is equal to 0.10799. F3, which is equal to 0.64 by 3 F2, this is equal to 0.02304. F4, 0.64 by 4 F3 is equal to 0.00047. F2, this is F3. Sorry, this is, I think this is, should be, F4 should be 0.00369. F5, 0.64 by 5 F4, which is equal to 0.00047. And probability x greater than equal to 6, which is nothing but a sum of x from 0 to 5 fx, and this is equal to 0.00006. Okay, so please check this value whether these things are correct or not. So now prepare a table. This is x fx. So 0, 1, 2, 3, 4, 5, 6 or more. And these probabilities are 0.52729, 0.33746, 0.10799, 0.02304, 0.00369, 0.00047, 0.00006. Okay, and expected frequency, which is equal to, here n is 250, n into fx. So see that this is 31.82. Frequency always an integer, so we approximate it to a closest integer, that is 132, 84.37, which is approximated by 84, 27, 5.76, which is approximately by 6, 0.92, approximately by approximated by 1, 0.11 is almost close to 0. Similarly, this one is 0.02, which is again close to 2. And if you add all this frequency, you see that total frequency is 250, which is obvious. So observed frequency here is, just write this thing, 140, 75, 25, 6, 3, 1 and 0. So if you look at this last two columns, that is column 3 and column 4, we see that expected frequencies are close to the almost close to the observed frequency. So we conclude that fitting is good. Okay. So please tell me, have you any queries? So is that is I write this conclusion. Comparing the expected frequency with the corresponding observed frequency is seen that the fit is quite good. Okay. So I think this part is clear for you. Okay, thank you, Pritam. So please tell me, have you any problem except Pritam, Monabo, Sumon, Ashtuto, anybody watching this video? Please tell me, have you any problem? Have you any queries or questions? Please tell me. So after 10 minutes, I will be back and start the another thing. Okay, Shashwat sir, for how much difference between expected and observed frequency? Can you say this? Okay, Shashwat, your question, you were asking right thing. Obviously, how much it is very difficult to tell you, okay? Because for the fitting, whether this fitting is good or bad, we need to uh, use chi-square testing. Okay, for whether this fitting is good or bad, we use chi-square test for goodness of it. Okay, otherwise, this is the this is your the basis of observation. You can just tell this fitting is good or bad. But see that 132 is 140 close. But if you think that there is, instead of 132, if there is 110, then it should be uh, not good as 132. If instead of 84, suppose it is 90, again this is not good. So it is on the basis of your observations whether this fitting is good or bad. But for appropriate conclusion, you need to test this thing. This is called chi-square test for goodness of. You use chi-square test for goodness of. Okay, so are you agree with me or not? Please tell me. This test you should this test hopefully you learn this test. I think third year, or I think third year, when hypothesis of testing is introduced in your syllabus, then you should learn this. But my in my today discussion, I do not discuss this part. Okay? You learn this after I think in third semester, sixth semester, maybe sixth semester. Okay? Thank you everybody. I will be back after 10 minutes.